Right, now we've got basic visualization out of the way, we're now ready to tackle ODR and how to apply it to physical data. So say we've got some measurements and we're trying to find out, say, the refractive index of air. Well, that would appear in our model, say Snell's law. So we would fit that model to our data, and then ODR would give us the best fit parameters, and that would therefore allow us to determine the refractive index of air based on our observed measurements and errors on our uncertainties. So for this example, I'm not going to use any numbers or any data. We're just going to get the bulk of the skeletal code out of the way, and then in the next video I'll apply that code to some real data. So to start off with, the first thing you want to do is define your model. So I'll keep this as generic as possible so you can make some skeletal code out of it. So let's call it model fit. So we're going to pass this beta and x, because we've got our independent variable x, which is our measurements. So let's call that y fit equals, now this can be any function of x because it all depends on what you're trying to fit. It could be a linear line, it could be a sinusoid, it could be an exponential, it could be all of those together. So let's just say, I don't know, let's just write it as f of x. Obviously we'll have errors here, but the point is to get the message across, and then we'll actually use the code correctly to determine some parameters. So the next step is the actual ODR code. So you can possibly change this name here. I just keep it as model. I've always kept it as that. This model has to be capital M because it's the one we've imported here, and this is whatever name you've assigned here, so they've got to be the same. So after that, we then use data equals, now we're using real data as a scientist, which just so the difference between real data and data, when you import them, it's all to do with how ODR treats your errors. So for real data, it treats them as 1 sigma standard deviations. So that's what I'll be using. So we've got data equals real data, so we'll have x data, we'll have y data, we'll have sx errors, and we'll have y errors, won't we? So again, you'll have to define all these names with NumPy arrays, what I use, so they'll contain all our errors from our experiments. But obviously, don't worry about all these. This is just because I haven't given any numbers. So we'll get the skeletal code done and then give it numbers. So after that, we'll say ODR equals capital ODR because that's the name of the package or module we've imported. So we'll have data and then model because that's the two things we've defined here. And then the next thing in square brackets is your initial guesses. So let's just leave this generically, guess 1, guess 2. So for ODR to proceed, you have to provide initial approximations of the parameters that you're trying to determine. So let's say f of x was of the form, and let's just leave it as a linear fit. So beta 0 plus beta 1 times x. So this resembles that of a straight line, y equals a plus bx. You can't write it like that because it has to be implicit that, because the beta array is the array that contains your parameters. So your parameters can't be random letters. It has to be implicitly like this. So beta 0 would be our vertical intercept, beta 1 would be our gradient. So guess 1 would then correlate to beta 0, guess 2 would correlate to beta 1, and so on and so forth. And another optional thing I put on is max it. Stands for maximum iterations. Only really comes in when you have multi-parameter fittings, like 3 or 4 parameters, because that's when it gets really tricky. So you can probably omit that and you'll be fine. But this here is mandatory. ODR won't proceed without that, so make sure you fill that in. Again, I'll illustrate it with a numerical example. Okay, after that is ODR.set underscore job. Then we have fit type equals 0. Now I'll write a little comment here. So we've got 0 for explicit ODR, 1 for implicit ODR, and 2 for ordinary least squares. So again, it just affects what kind of fitting you're trying to do, and it also affects how it treats your errors, your standard deviations in the errors. I always use 0. I'm not the most experienced statistician, so I can't comment on these, but I only really have experience in using 0 for explicit ODR. I can't comment on the other two, but you know, they might come in handy depending on what you're doing. So the next line of code is output equals ODR.run. So that just runs the code. Then we follow that with output.pprint. That isn't a typo, that's supposed to be another P there. It stands for pretty print, because when you run it, it will print all the numbers down here for you. And then final two lines, we have beta equals output.beta. And let's say beta error equals output.sd underscore beta. So what these two final lines do, this prints out our beta array, so that contains our best fit parameters. So in this case, it would print out our best beta 0 and our best beta 1. And then the same for beta error, it will print the corresponding 1 sigma standard deviations. So it will not only give you the best fit parameters, it will also give you the errors. So that's the basic skeletal code that I will always use. I copy and paste this chunk here every time, and I just replace the variable names and the errors and the guesses. So that's it for the basic structure. We'll then move on in the next video to a numerical answer to actually use this.